Hi, so today we are going to learn a microscope and a telescope, which is a topic in ray optics. Our eye has certain limitations that we cannot see very tiny objects, small objects. We cannot see unicellular organisms. We cannot see an atom or molecules because of certain limitations of our eye. So for viewing those objects, we take help of optical instrument which is called a microscope. Now, a microscope can be very sophisticated one which are used today, but we are going to discuss a simplistic form of microscope and a simple microscope and a compound microscope. Simple microscope is also called a magnifying glass. So a simple microscope, which is a single converging lens with small focal length. You will further come to know while learning that magnification will be very large if focal length is small. So firstly we will start with simple microscope, your magnifying glass. So for magnification with the help of a simple microscope, a magnifying glass, we put an object at a place near to focus or within focus along one side, and the object is viewed from other side, keeping your eye on the other side here. The object is viewed such that the image is formed in between a distance which is 25 centimeter away from your eye and up to infinity. Because our eye has limitations, we can see clearly a range of distance which falls in between your 25 centimeter from our eye up to infinity. This distance, smallest distance which can be seen clearly, 25 centimeter from our eye, this distance is called near point. So what is near point? Near point is the nearest distance from our eye which can be seen clearly from ourselves. And for a healthy person with a normal eye, this near point is 25 centimeter. Similarly, the farthest point which can be seen by ourselves is called far point. And for a normal eye, for an adult person, this farthest point is infinity. So we see a range of distance from near point up to infinity. Now you will notice while seeing a very far object, like any building or like any tree in an open field, that your eye is least strained. You just leave your eye and you see. There is no strain in your eye. But when you read something from any newspaper or from any paper, you will find that some strain is felt. So when object is at near point, you will find when image is at near point, you will find that image is largest, most magnified, but your eye is strained. And when image is at infinity, your eye is least strained. When image is at infinity, normal vision, and eye is least strained, and you can feel it. It is a matter to feel by yourself. So now we will discuss magnification through this your simple microscope or this your magnifying glass, and this magnification is linear magnification. Magnification by a magnifying glass or a simple microscope. Now the simple microscope is only a converging lens, and you know that magnification, linear magnification, M is equal to V upon U. Here you have V placed at near point, so I'll replace this V with minus D. But firstly I am going to convert this U in terms of V and F. Using lens formula, you know that in a lens formula, you know that 1 by V minus 1 by U is equal to 1 upon F, and therefore 1 upon U is equal to 1 upon V minus 1 upon F. So I am putting this value in equation 1. So in equation 1, your magnification is equal to V into 1 by V minus 1 upon F, and therefore magnification is equal to 1 minus V by F. Now let me put the value of V. As the image is obtained at near point, so here V is equal to minus D, because image is obtained on the same side of the U. So this distance, when you will measure starting from optical center, it is in a direction opposite to direction of incident ray. So this should be taken as negative. So since V is equal to negative, therefore M comes equal to your 1 minus minus plus D by F. So this is the magnification when image is formed at near point. Now I had told you that focal length of this converging lens, this magnifying glass, simple microscope, should be smaller. So from here you can consider this, understand this. M will be equal to 1 plus D is your 25 centimeter. Now if you take focal length small, like 5 centimeter, then magnification of this magnifying glass is 1 plus 5 means 6. 6 times the image will be magnified with respect to object. If you further reduce the focal length, like you change the focal length to 1 centimeter, because a converging lens can be obtained with smallest focal length is nearly 1 centimeter. So in that case magnification will become 26 times. So magnification depends on focal length. So while using any converging lens as magnifying glass, as simple microscope, we should take the focal length of the converging lens small, then only magnification will be large. So this is the case when final image is obtained at your near point. Now when final image is obtained at far point, at infinity, then by this way you cannot find magnification. You cannot find, because magnification is equal to V by U, and when V becomes infinity, so you cannot find a magnification in this term. Magnification is lost by doing this, your linear magnification. So we will be doing angular magnification. For finding magnification of image when image is forming at infinity. So for angular magnification, we need to know a visual angle. What is visual angle? Suppose you are seeing any tree which is very close to you, just beside you, then you will find the image of this tree or any object is forming on your retina, and this is the size of image. This image is just acting on rod and cone cell. The light reaching here up to this area will activate the rod cell and cone cell of this large distance, large length. So image will be large. Now if the same tree is placed very far from you, imagine just in an open field that the same tree is very far from you, so the tree will appear very small. And why it is appearing small? Because the image is forming on your retina on a short distance, short length, short area. It will activate small number of rod cells and cone cells. So image will be small. Now the object is same, but you can see the size of image varies. So image depends on, from here you can find that size of image depends on this angle which is made on your eye. If angle is large, then image will be large. If angle is small, then image will be small. So from here you can see that this visual angle is very important, and for magnification you can compare the visual angle also. So what is angular magnification? Angular magnification is angle produced by an object at eye with lensage. With lensage it will be making large angle divided by angle produced at eye, naked eye, angle produced at naked eye. So magnification, this is your angular magnification. Is angle made. So angular magnification produced at our eyes by the rays coming from object is equal to angle made at our eye when we are using any visual aid, any convex lens, divided by angle produced by the object at our naked eye. So magnification is equal to theta upon theta naught. So this we will be finding. Here in first diagram you can see we have not taken any visual aid. So we will find the angle it is making, the object is making at our eye. And from here in this triangle, right triangle, you can write that tan of theta naught is equal to perpendicular upon base. But for small angle, you can write tan theta nearly equal to theta naught for small angles. And therefore theta naught comes equal to h upon d. Now similarly we will find angle theta in this very case when we have placed object at focus. So similarly you can write that angle theta, here in this case you can see theta angle is forming. This vertically opposite angle also should be theta. So similarly theta is equal to perpendicular h by base f. And this is the case of normal vision, because final image is forming at infinity. And this is a real image because the ray will be meeting at infinity. This is a case of normal vision. We could not obtain magnification for the normal vision with linear magnification. So this we are doing with angular magnification. Now, angular magnification is equal to theta upon theta naught, and this is equal to theta has come h by f divided by h by d, and this is your h by f into d upon h. So magnification comes equal to d upon f. You can compare magnifications in the two cases. You found that magnification when image was formed at near point, this magnification comes 1 plus d upon f, and when image is forming at infinity, then we find that magnification is equal to only d by f. So image will be most magnified when object is placed at near point. When image is obtained at near point, and when image is obtained at infinity, then you have magnification equal to d upon f. So this is about the magnification using a simple microscope, any converging lens. Now we will also find magnification, angular magnification, when object is not placed at focus and when object is within focus and image is obtained at d. So magnification is equal to theta upon theta naught, and this is your equal to theta you can obtain from here. Let me find theta. Theta is equal to perpendicular h upon base your u only, and theta naught, when you have viewed it with your naked eye, with lens, and theta naught, this is with lens, ul with lens, and theta naught without any lens, it will be equal to your image height by d from here. Theta naught is image height by d. So now magnification, therefore magnification is equal to your theta. Theta is h by u with lens divided by theta naught, that is h by d, and this is equal to h by u with lens into d upon h. H and h is cancelled, therefore magnification comes equal to d upon u with lens. Now let me find the value of u with lens using lens formula, since 1 upon v minus 1 upon u is equal to 1 upon f, and therefore we find that final image is forming at near point d. So we can use v is equal to minus d and u is equal to minus u with lens, because both are on the left hand side from optical center. So putting these values, we get that 1 upon u with lens is equal to 1 upon f, and here minus 1 upon d, when it goes on this side it will become 1 upon d. So in place of 1 upon u with lens, we'll be putting this value in equation number A. So therefore in A we can find magnification. This is your d into 1 by f plus 1 upon d, and therefore magnification comes equal to 1 plus d by f. So same magnification can be obtained when final image is obtained on near point by linear magnification and by angular magnification. So this is all about your simple microscope. Now a compound microscope. A compound microscope, in a simplistic version, we use two convex lenses, both with small focal length, and objective is having still smaller focal length. So a compound microscope is one in which we use two convex lenses with small focal lengths with objective is having still smaller focal length. Now the working principle and construction of a compound microscope. A compound microscope consists of lenses. So it will work on the principle of refraction of light. And it will work on magnification of image. Now construction. You can see that the two convex lenses are kept coaxially. They are kept in two different barrels such that the distance between the two can be changed using a rack and pinion arrangement. In order to have final magnified clear image, we change the distance between the two lenses. So this is simple description of a simplified version of a compound microscope. Now we need to find magnification obtained using a compound microscope, magnification in image. So we know that magnification using multiple lenses is equal to product of the magnification produced by the lenses. So net magnification will be equal to magnification produced by first lens into magnification produced by second lens. And here we have second lens which will be acting as a magnifying glass, a simple microscope. So its magnification when final image is formed at near point, we have just obtained. This magnification M2 you can write is equal to 1 plus d upon focal length of this lens. And this lens has focal length Fe, focal length of eyepiece. So magnification due to second lens we already know. Now magnification due to your first lens, m1 is equal to image height upon object height. Now we have two similar triangles, your ABO and A dash B dash FO. In similar triangles, ABO and A dash B dash FO, you will find that ratio of the sides will be same. So H dash by H will be equal to B dash FO. M1 is equal to H dash by H is equal to B dash FO divided by your OB. And now I'll put the value of B dash FO and OB. OB is your object distance which is on the left hand side. You will measure this distance just opposite to direction of incident ray. So you should take this negative. And this distance is nearly equal to focal length of objective, because object is placed near focal length of objective. So therefore, this distance can be written as minus FO and B dash F. B dash FO, here it is taken as length L. In a compound microscope, the focal length are nearly very small, nearly 1 centimeter or so. So this length is negligible. So the remaining length is called the length of the compound microscope, and this is taken as L. So this distance can be written as L. Now therefore M1 is equal to L by minus FO, and therefore net magnification, which is equal to M1 into M2, this becomes equal to minus L by FO into 1 plus D upon FE for your final image which is forming at near point. So this is magnification when final image is forming at near point. Now second arrangement, in which final image is forming at infinity. So again you have two magnifications and they will be multiplied for net magnification. Net magnification is equal to M1 into M2. Here M2 for normal adjustment. For normal adjustment, and normal adjustment is when the final image is forming at infinity. So for normal adjustment we have just obtained M2 is equal to D by focal length, and focal length of eyepiece is FA. So net magnification we can obtain in terms of M1 and M2. So therefore let me write M1, we have just obtained. M1 is equal to minus L by FO, and this M2 is equal to D by FA. Therefore net magnification is equal to minus LD upon FO FE. So these are the magnifications in two cases. When final image is obtained at infinity, you have magnification minus LD upon FOFE, and when final image is obtained at near point, then magnification is equal to minus L by FO into 1 plus D upon FE. So this is how you can magnify the size of image for viewing small objects using microscopes. But you can also improve the quality of image, which depends on various other aspects also. Like if object is illuminated in a better way, then the quality of image will be good. Image will be more bright and clear. And if you are using multiple component of lenses for objective and eyepiece, like you are not using a single lens, then also the quality of image can be improved, as all kind of aberrations like your chromatic aberrations, all kind of lacking in the image can be removed by using multiple component of lenses.